Thanks, Robin, and thank you to everybody for the bitter end of this session. I appreciate it. I'm here today to present the work of my recent PhD student, Tim Pearson, who wasn't able to travel to the conference. And actually, if you were there at MobiCom, you may have seen me on stage again presenting the work of Tim in a paper called Close Talker, which is actually very much related to this one and motivated by the same challenge, which is our expectation that billions of IoT devices are going to be deployed in the next few years. And many of those IoT devices don't have a typical user interface, like keyboard, a mouse, and a screen, which you might use for entering a password or a PIN code or something like that to help get the device connected to a network or to other devices. And the fundamental challenge that we're interested in is getting two devices that have never met before to talk to each other and to establish some kind of a secure relationship that allow them to wirelessly communicate over time and over space. So a smart speaker and a television, or a heart rate monitor and a treadmill, or a light bulb and a light switch. You want them to establish some kind of relationship so that one can talk to the other. And we believe that proximity can be a useful basis of trust. And so what does that mean? If you have two devices and one of them sends a message to the other saying, here's my passcode or a secret key or something, and you can use this for securely communicating with me in the future, why should the receiver believe it? I mean, an adversary might be there and sending its secret key or password and spoof the receiver into connecting to the wrong device. So proximity, we believe, can be useful. I can take two devices and hold them next to each other, even temporarily, and allow them to communicate over short range to exchange that information. That's what Close Talker does. That's the MobiCom paper. But now the challenge is the receiver is getting that information and has to decide, is this coming from a close-by transmitter or a far transmitter? And by close, I mean a few centimeters, and by far, I mean more than this far. So any adversary that's beyond this sort of range is considered too far to be trustworthy, and that's why I, as a user, can hold them and say, I want these two to be communicating with each other. Others have determined methods for proximity detection, but they all require multiple antennas. So the cool thing about this work is that a single antenna Wi-Fi receiver, standard hardware, can decide whether a transmission it has received comes from close or far. And the technique depends on two tricks. The one is Wi-Fi specific. And if you think of a Wi-Fi frame, it has a payload, it has a header, MAC header, and it has a preamble. And that preamble is mostly a phi layer thing used with a physical layer to do channel estimation. And one of those fields is called the long training field, and it has two subfields called T1 and T2, each of which is 64 symbols long and identical to the other. So 64 symbols and then the same 64 symbols repeated again. They're a static, standard set of symbol values that every receiver knows and looks for. We're going to watch to see that those are the same or whether they're different. If they're the same as normal in Wi-Fi, then we actually believe the transmitter is far away. And if they're different, then the transmitter must be close. And here's why. And the second trick of this approach. It depends on radio physics. So in the middle of this circle here is a vertical bar, and that represents the transmitting antenna. And of course, radio waves emanate outwards from an antenna. And radio waves are electromagnetic waves. And normally, in the range that we normally operate, those are kind of radiating out nicely and spherically. But if you're really close to the transmitter, like within a couple of centimeters, you're inside what's called the reactive near field. And there's a lot of energy there that actually doesn't radiate out. And if you're receiving inside that little bubble, you actually get a lot of noise. And that noise, that rotating electromagnetic field, causes the phase of the received signal to be different. And out to about 14 centimeters, you can observe that effect. So let's take a look. The way radio physics people plot their results is often on an IQ diagram in a two-dimensional complex space. And on the right-hand side, you'll see a graph of a 30-centimeter transmission. So the sender is 30 centimeters from the receiver, and we would expect all of the samples from all the subcarriers of that frame to line up on one of the two red dots, and sure enough, they do. But if we bring the transmitter within 6 centimeters of the receiver, then they're all over the map. That's because of that reactive near field extra energy that's causing the phase to differ across the different subcarriers. And so we can measure that, and we can measure that error, how far are those green points from the expected locations, and come up with a metric. And so here I have a plot of various tests. On the x-axis, we have the distance between transmitter and receiver from 2 centimeters to about 3 meters. And on the y-axis, we have that error metric. And as you can see, there are 4 curves, and each of those curves represents a different antenna being used to transmit. We just bought some cheap, typical Wi-Fi antennas to do the transmission off the shelf. And there's some differences between the antennas, but they all tell the same story. On the far right side, when you're more than 14 centimeters apart, you see almost no error. And on the left side, when the transmitter is really close to the receiver, you see a high error. So we picked a threshold of 0.2. And any error over 0.2, we say, that's close. Any error below 0.2, we say, that's far. And notice we never make a mistake if the sender is more than 14 centimeters away from the receiver. Occasionally, we'll make the wrong decision when the transmitter is close, but you could send 2 or 3 frames and just do sort of majority voting or something like that to increase the confidence. So this works pretty well. It's pretty robust and very secure. Except, what if you have an adversary who really wants you to believe that he is close when in fact he's far? So the adversary could use an SDR to transmit a frame with a preamble where T1 and T2 are different. You can control everything, right? So that would fool you. So we have 2 techniques that you can layer on top that protect you in that case. In one case, the receiver, let's suppose, has a trusted device. It's already associated with the router in the home or the office or what have you, and it trusts that router for all kinds of things, like sending internet traffic. If it receives a frame where it sees T1 and T2 different, it could believe the transmitter is close. But it could say, hey, router, did you get that frame? And did T1 and T2 differ for you too? Well, if it did, then that means there's some distant adversary that is faking T1 and T2. But if it didn't, if it received a transmission where those are equal on the router side and different on the target side, then it probably means the transmitter is close to the router and not to us. The other method, which is complementary, is to use signal strength. If a transmitter is close to you and T1 and T2 differ, you think, well, I must be in its near field. But another thing should happen. It should be a very strong signal, right? And so if it's a weak signal and T1 and T2 differ, that's probably an adversary who's not close. Okay, now let's let the adversary go even further. The adversary gets a big directional high gain antenna and cranks up the transmission power so that your receive signal strength is high. Well, okay, how hard would they have to work to make that happen? This table shows you for various gains of antenna and various distances. The first one is just 1.5 meters. How high would they have to crank up the transmit power for us to believe that they are close? Well, those gray areas are where they could succeed, but to do so, they have to crank up their transmit power more than 4 times the legal limit to achieve to fool us. So we believe that this raises the bar pretty high for an adversary. They have to have a very high gain antenna that's about this big, and they have to be within 1 meter or so of us, so it's pretty noticeable, and they have to break the law by going too high on the transmit power. So overall, SNAP, as we call it, is a nice, simple, robust, secure way of detecting whether a transmission is coming from a close transmitter. And you could use that then for lots of purposes, and we use it, for example, as a basis for deciding whether to trust that transmission and then using techniques like close talker to begin a secure relationship. And with that, I'm happy to take any questions, and of course to defer the really hard questions to Tim, who'd be happy to give you more detail. Thanks a lot.